let's get started. So first, who are we? I'm Daniel. I work in product marketing here. Might have seen me if you've been on webinars before. You might have seen me. I originally was a mechanical engineer, and I joined Markforged about 7 years ago now. I went in a really small company when our biggest printer was the Mark II. And I've kind of slowly transitioned from engineer more towards strategic marketing and storytelling and that kind of stuff. And I tend to lead all of our efforts on FX20 and then on some other platforms that we work on as well. So that's my background. I love talking about 3D printing and have kind of been with us the whole journey. So it's been exciting to see us grow.
All right, I'm Doug Piazza. I'm the application engineer for the Midwest. So I cover the central time zone. So mostly dealing in pre-sales and helping our existing customers as well as new customers figure out where to find value within their business using our platform. But I'm no stranger to Markforged. I've only been here about a year, but I was a longtime customer before joining Markforged. So definitely accustomed to the platform, and that's what brought me here today. So looking forward to it.
Yeah, Doug's selling himself short. He was a super user, not just a customer. But yeah, so we're going to keep it pretty simple today. We're first, for the unacquainted, I'll give a super quick intro on FX20. It's been out for a year and a half now, but maybe y'all haven't seen some of the details of it, and we'll go from there. Then we'll talk about our strengths in tooling generally, and then we'll talk about our killer applications that we've kind of spec'd out here. And today we're specifically focused on more Onyx-centric tooling, so more low temperature type tooling, but there are high temperature tooling applications out there. Just for the sake of this one, those are the applications we ended up kind of zooming in on. So first, super quick intro to FX20 for those who don't know much about it. It's Markforged's newest next generation FFF printer. It launched in 2021. Technically, it formed next, but we started shipping it last year. It's about 100 or more than 100 to about 20 countries. So it's shipping globally. Reception for it has been positive, and it's the first printer that is both continuous fiber or CFR, our unique technology, and high temp capable. And kind of the onus for us when I talk about this today is that when people see kind of high temp capable printers, they instantly think aerospace or parts on airplanes or stuff kind of along that side. But we see in-house and we see in a lot of customers is that a lot of them purchase it for tooling and they love using it for tooling, and the same benefits that apply often to our smaller printers, say our Mark II and our X7 and kind of typical manufacturing grade printers, are actually amplified by FX20. So we're going to talk about that today and kind of get a little bit deeper into that. So I want to give a super quick tour of the machine because it's pretty different than a lot of the other printers that we sell and also that you'll see in the market, especially in the FDM space. By nature of being high temp and larger, but still need to be precise. So super quick, it's about 525 by 400 by 400 build volume. For the non-metric incline, that's about 20 by 16 by 16. It has heaters on each side of the build chamber, and they basically enable to heat pretty precisely up to about 200 C in the chamber. Ultem prints really, really hot, and this is an Ultem capable machine. Onyx, it prints typically closer to room temperature, although if you print it in the faster print modes, we actually heat up the chamber to about 75 C to print it. It has a vacuum bed with a basically reusable print sheet. It's pretty simple to use. I use it all the time. It's very, very easy. And it's highly automated. So all of the leveling and nozzle offsets and that kind of stuff is done automatically. You kind of just click print, it calibrates itself, and then it starts printing. If you need to move it, you can do basically factory relevels. It's not that complex. I've done it a bunch of times. But yeah, so it's a machine that's kind of built to be used in a factory setting. That's the goal. The print head is a bit different than kind of most FDM print heads you'll see. It has basically 3 discrete modules on the larger head. The 2 flanking modules on the outside, both are plastic printers. So this machine actually can print 2 different plastics at the same time. That's very useful for Ultem because you need a dedicated support material. We have not done anything else with it yet. We might do soluble support or something like that in the future, but for now, that's just a capability we have for Ultem. But each of those nozzles is plastic. They're direct drive extruders. The module itself kind of contains all of the printing engine within it. And the central one is the continuous fiber. So the stuff, the technology that we're known for, that we are kind of specialize in. So this machine is CFR capable, but also has multiple polymer things. And the nozzles are very different than our other nozzles. They're extremely wear resistant. So they don't wear out day to day. You don't see kind of that type of typical nozzle wear. They still might clog and jam if you do something wrong. But it's a little bit different than our typical thing. You'll see this printhead is much larger than our typical printers. The printhead itself weighs like 5 or 6 pounds. It's a more hefty machine. And what moves that printhead around is an enormous motion system. Essentially, we rebuilt all of our motion system from scratch from any printer we previously designed for this. And there's 2 reasons for that. The first is that it's a high temp printer, so you have to deal with the machine expanding and contracting as it heats up. And the second is it's much larger. As I said, the printhead's super heavy. So you can see here, there's basically 2 servo motors driving that big gantry and then a servo motor on that. More exciting for y'all is that there's linear encoders on each axis. So the machine knows exactly where it is at all times. When you use something like a rotational encoder on the servo, you're interpolating the belt. What the belt is basically the error between the belts and the motor itself. And you don't want that if you want a really precise machine. So all of that enables us to build an extremely precise closed loop control algorithm, which enables us to move really fast with a really heavy print head and still keep the precision that you expect out of a Markforged machine. So that's the exciting part. It also is separated from the print area by baffles, and you can see on this in this kind of CAD cutout that there's vents out the back. So that's how it keeps the print area, basically the gantry area, cool while keeping the print area hot. One exciting thing here is the material cabinet that we haven't really talked about. It's very different than other machines. You know, we source 4 spools. There's basically 2 spools dedicated for each nozzle. And we're still working on, but we'll complete pretty soon, this ability to change over automatically between these spools. The spools themselves, if you're a Markforged customer, are 4 times larger. So they are much larger. This thing can chew through an 800 cc spool in about 12 hours or less if you really have it printing fast. So the 3200 cc spools are pretty necessary. And I've printed parts that are more than a 3200 cc spool, but that starts to get close to the whole build area. You still use Desiccant packs for moisture control, but there are moisture sensors in each bay to determine that to make sure that there is a acceptable level of humidity. In terms of material availability for the machine, it is a kind of a smaller subset of our base materials. We're working on expanding that, but we're focused primarily on reliability and delivering quality print experience with Ultem added. So basically, we have, what I think about this is we have 3 base plastics, Onyx, Onyx FR, and Ultem 9085. And each of those has a requisite carbon fiber that typically goes with it. So Onyx, you can use your typical carbon fiber FR works with Onyx FR. And then we have this dedicated carbon fiber for Ultem filament, which is a special carbon fiber that is designed to work with Ultem and other high temp materials. And that enables us to reinforce high temperature parts. It's a really interesting capability, something that is totally unique among 3D printers. So yeah, super quick into strengths and tooling without taking the intro too deep, and we'll talk applications in a second. So this is a really simple slide of why is FX20 good for tooling? And you'll see here a lot of these benefits are kind of a mix of things you'd expect from smaller printers with a little bit more added. So the first is that, simply put, and this is an easy one, is that it's really large and it's really fast. For a manufacturing grade precision printer, a printer that's printing precision parts, this thing is really large. There are printers larger than it, but in its class, it's a pretty big machine. It prints at about 40 cc's an hour. If you're looking for those exact numbers, the more like kind of back of the envelope numbers is it prints about a spool in about every 12 hours. So you can imagine how quickly it moves. And typically its default print layer height is 250 microns. Although I will say that the quality at 250 micron for this machine is relatively comparable than the typical like 100 micron default print height at like a desktop machine. So this thing prints really high quality really quickly, and it's still really accurate. And so those two things combined mean that you can print parts quickly without sacrificing quality. And that's a pretty common trade-off in additive is, the faster you print, the lower quality the end article is, and we really didn't want that for this machine. Second is it's CFR compatible. So we're familiar with CFR, its ability to lay long strands of fiber within parts. This machine is compatible with it. It provides critical stiffness. And one place where this really is important on these is parts with large aspect ratios. So you'll see a couple examples here, but essentially parts that have basically are large and flat or long and thin. those type of parts are extremely challenging to print like without like continuous fiber reinforcement, because plastic is basically constrained by how strong the plastic is. No plastic's really strong enough to withhold like forces on a long flat part. So this really helps with both the part performance and then also the print performance. Plastic adding fiber mitigates warping to an extreme degree. So you can print these large flat geometries and not worry about the parts warping. So that's a really nice and important feature. And then the last thing I'll note is that because of our technology we launched last year, which is basically the ability to section parts and do custom settings in each section, you can reinforce individual features of large parts. So while fiber starts to kind of look a little less practical on like a huge, giant, blocky part, to put it not very precisely, when you might have a single aspect of that part that's really important to reinforce. And so with the technology, you can still just reinforce the one part of the aspect of the part you actually need while still printing the rest of it. And the last one is pretty common to 3D printing, but I think it's still worth noting here because on this scale, it's extra unique. The free complexity. So free complexity enables really is kind of two things. The first bottom up is it costs no more to produce a complex geometry than a simple one. So if you have something like some of these applications you'll see here where they are really complex and difficult to make, typically in a manufacturing operation, that would mean that these parts are more expensive to make. And with these applications, they're not. It's costs the same to print them as it does to print a block. In fact, sometimes it's cheaper because it's less material. And the last thing is it enables really unique features like internal channels or captured segments or specialized infill or all these things where 3D printing is the only thing that can do that. And putting a high quality machine that's capable of printing parts like this makes it much more valuable, makes those things much more valuable. So yeah. So those are kind of the basics of strengths for tooling and why we talk about FX20 in this way. Now we're going to run through a couple applications. Doug will lead off with a couple. I'll take the last one. Then we'll run to questions.
All right. Thanks, Daniel. So we're going to get into the meat of the presentation here. So first one we're going to talk about is casting. And I think in my experience, this is not one that we've given a lot of attention to as far as use cases and case studies go, but I think it's an excellent use case for our technology and one that I'm seeing our customers in the Midwest using a lot of and having a ton of success. So I think it's best to just take a step back and understand what does the current state of casting look like, additive aside, what's going on in that industry. So casting design has come a long way. They're getting more and more complex. The drive to use less material and get better performance characteristics out of them is what everyone is pushing for today. So the days of blocky castings with not a lot of features isn't really the case anymore. So complexity is increasing, but the methods in which we're making the tooling for the castings hasn't really changed a lot, kind of since casting started. So the picture on the top right you're looking at is a wooden pattern. So this is traditionally how castings have been made forever. Someone carving wood, cutting, sanding, adjusting it in order to get the correct shape, as well as dictate how the metal is going to flow into the mold itself, which is very important and one of the things we're going to talk about. But this really hasn't changed too much. So sorry about that. So prior to simulation, and I'd say even this is still happening today, the stage of going from design to tooling is a little bit of an art. So you don't always get the results that you want when you make the tooling. And that requires people to go back, make adjustments. And mind you, a lot of these are being done by hand by tool makers that are sanding certain parts of the casting, trying to change dimensions of it to get it to perform properly. So in more recent years, that's changed in the sense that tools like simulation have come around. So on the bottom left-hand corner of the screen, you're looking at a casting simulation. So molten metal being poured into the mold and then analyzing how that material is going to flow through it and also how it's going to solidify. So those are very important things. But translating those results from the simulation to the real world is proving to be challenging. And that's because there is this manual step in between. So where we've kind of come in and said, maybe there's a better way here It really comes down to taking the optimized designs from simulation and printing them directly and having the confidence that they're going to be correct. So Daniel, if you want to go to the next slide. So here's a look at one half of a match plate casting pattern. So the light gray is obviously one half of your part, but the darker gray on the outside, that's representative of what we would print. So that's gates, risers, runners. Those are really critical aspects to how the casting is going to be made. So how that molten metal is going to flow through those channels is going to dictate part quality, accuracy, and many other factors. But by having something that you can rely on, that you can take those simulation results and go directly to printing, it takes out a lot of the guesswork and also all of the manual labor that these tool makers are typically doing. It's print, install, go and test. So I think the real benefit here, you can see lead time is the big one. If you can make your tools overnight, essentially in 12 hours, that's a huge benefit to your operation. I mean, cost and driving down the P&L is always important, but I think in the world we live in today, time is everything. The faster you can deliver to your customers, the better off your business is going to be. So that's casting at a high level. Daniel, if you want to go to the next slide or add anything. You're on mute.
So these are typically Onyx only parts, yeah? Doug,
Correct.
Yep. And what do you say, like, I guess from your perspective, like, what is the resolution required? Like, what do you typically see as needs for these? Like, how does 3D printing fit well in that space beyond just fit the kind of requirements beyond just kind of being a faster technology?
Yeah. So for gates, risers, and runners, most people are printing them at 250 microns. So the fastest print setting that we have on FX20. So that's why you're able to turn around that tool in 12 hours. If you want to make the, half of the part itself for the pattern, you can use a lower resolution, like 100 microns or 50 microns, where you're going to get exceptional quality directly out of the machine and not have to post-process it in order to get a good surface finish on the part. So I'd say both, right? High resolution for parts themselves, lower resolution for the tooling on the outside of the parts.
Yeah, and also, I mean, just the size of this part, it's like 20 inches across and 15 inches in that direction. Obviously, it's kind of a long, snaky, like kind of narrow part, but like half a day is pretty impressive for that type of that type of size of application.
Yeah, I mean, compared to the traditional people making them out of wood, putting Bondo on them, sanding them, it's a much better process that yields better results, like top to bottom, pretty much.
Mm-hmm. And I guess one more question for you is when you introduce this casting companies, it sounds like, they're typically running with legacy operation with probably very skilled, like almost artisanal tool makers, right? Yep. Because people are making this. What's their reaction when you introduce like this type of technology to them?
Some embrace it. Some are, this is going to make my life easier. Others are, I know what I know. I want to stick to it. But I've even seen that change over time with some of our customers. It's just recognized as a better way of doing things, and over time people ease into it and adopt it more. But from an engineering perspective, I'd say adoption is pretty easy. People kind of just understand the value that it brings.
Awesome. Well, yeah, let's kick to the next one.
All right, so next one is broad. We're going to talk about automation. So in general, when I think of automation, I think customizability. Every automated solution is custom made for the parts that you're trying to make. So, what comes out of that, right? You need a lot of tooling. For every single part you make, there's very rare chances where the tooling is going to cross over from part to part. So you're having to have large tooling sets to accommodate all the different things you want to run through that piece of automation. And then on top of that, it's expensive. This tooling is one-off, it's pricey. You're typically outsourcing for it, going to job shops or machine shops. And I would say everyone's outsourcing these days for the most part. So lead times are long. You don't really get parts when you need them. You get them when you get them. So pain points, ultimately it's gonna slow your time to market. So if you're trying to incorporate a new product into manufacturing, this is going to slow you down. It's going to raise costs of the projects. And then conversely, once it's in production, things break, lines go down. And those are obviously critical situations where you're losing time, you're losing money, you're losing production. How can you how could you make tooling faster to get you out of those situations? So those are kind of the two main areas that we're trying to address: is how do you get to market faster? And then how do you get out of those line down situations?
For sure.
And then, just looking at that picture before, where are the applications? And I'd say that they're plentiful. If you look at part fixturing, part clamping, gripping, bracketry, cable management, I mean, the list goes on of all of the areas that we know our technology plays really well in. And, a lot of it comes down to part accuracy, part strength, all of the things that our continuous fiber really brings to these different applications. We go to the next one, Daniel. So here's an application that is one that I'm seeing more and more of. And again, automation. There's so many different types of end of arm tooling. I mean, it's really a broad subset. But for this presentation, I just wanted to show what vacuum end of arm tooling looks like, because designs are getting more complex. A lot of people are using additive within injection molding, thermoforming, sheet metal stamping and forming. I mean, the list really goes on. And I think all of those industries could stand to benefit from end of arm tooling that's made on our system. So you have a very complex part here. It could be a stamping, could be an injection molded part, but the ability to create a tool that's specifically made for that part, it's going to help you run a smoother operation. You're not going to have as many drop parts. It's specifically made for the geometry of the part itself. And if you're looking at this design, it's really not able to be made through traditional means. This is specifically designed for additive as well as on our system. So, and like Daniel was saying earlier, thin cross members or high aspect ratio parts like this, fiber is going to help you tremendously in these applications. So if you're just printing this with plastic, chances are it's not going to be stiff enough. So adding a little bit of fiber to this part is going to go a long way in stiffening it and making it more robust for the application. So, and then on top of that, cost and lead time, the two main factors we're thinking about. So in the matter of a day, you can turn around a custom tool for your operation in order to get either a line back up and running or to introduce a new part into production. Anything you want to add, Daniel?
Yeah, I guess, Doug, you talked about this would be impossible to, like, the single part would be kind of impossible to be made without 3D printing. In your experience, if you have a typical vacuum tool, because these parts are made, right, like without 3D printing in large numbers, like what is the process for that? It's obviously a large assembly, right, with multiple, I assume, custom CNC machine parts and specialized hardware. Like what's it kind of look like when you're implementing something like that?
Yeah, I mean, the current state is, like you said, there's a lot of different ways you can do it. It is a combination of many things, machine components, but in a lot of situations, it's almost like an erector set. You're taking 80-20 or aluminum extrusions, trying to bolt them together to be configured for this specific part you're trying to make. And obviously, that's not ideal. It's not purposely built for the parts you're making. So, you get into situations where things are coming loose, it's not really holding up, and the part is not presented to the tool in such a way where it's going to grab onto it the best way possible. So obviously having a part that's printed in the geometry that you're trying to make is going to be the best solution. So
yeah, for sure. And I guess one more question for you, like, you could 3D print this in a lot of different parts. Like what's the advantage of printing it in a single body and consolidating it?
I think it's just in the essence of consolidation. If you have one part versus many, it's going to be more robust, it's going to hold up longer, and there's going to be less points of failure over time. I mean, you add more components, those are more things that are going to go wrong over time. So anytime you can reduce complexity, it's going to benefit you in the long run.
Yeah, it's awesome. Yeah, so I kind of led into the next one, which is mine. But let's talk with the last one, this last kind of application, and there are many more, and we can kind of answer questions about applications afterwards. But let's talk inspection tooling. Now I'm specifically talking large inspection tools. So large inspection tools are one of the hardest things to make reliably because they require both size and precision to basically make a successful tool. And so that means that you kind of in typical manufacturing go in one of two routes. You go, as Doug just kind of mentioned, the erector set route, right? Where you have a bunch of kind of standardized COTS tooling that you bolt together, and then you create customized fixtures, and it requires a ton of tuning and a ton of time. And even in that moment, is it actually customized or does it work well for your part? Hard to know, especially if your part has a curved geometries or something that's customized. The other way you can do it is you can CNC mill custom tools, and that's very accurate, but also extremely expensive. So 3D printing for a long time has been an extremely strong fit for this inspection tool market because it kind of combines the best of both of those. It's cheaper by nature. The parts are not that expensive, but you can get this high level of complexity. However, it's basically limited by the size of the machine you're working with. And inspection tools need to be, there's something that's interesting because they don't need to be that strong, but they need to be extremely stiff. And the reason, of course, is that if you have an inspection tool that is deflecting when you're putting something on it, it is not an effective inspection tool, right? It doesn't actually enable you to measure it or enable you to check like if it fits or not. So you need something that is stiff enough to not deflect at all, or to deflect an extremely limited amount when you basically place the article on it. And that's why machines like Markforged machines have typically been great fits for this, is because we print really strong, robust parts that don't deflect that much. And if you look to the right here, this is an example of one of our customers, Daco, who use an X7 to print basically this like 7 or 8 part assembly for inspecting basically a bunch of an assembly of hoses and housings around it. So that's why it has all these tube routing fixtures and things that look really complex and would be typically almost impossible to inspect. And this is something that they used a ton. So this, for reference, this aluminum breadboard is about 2 feet by 18 inches. So it's a really large breadboard, or 600 by 450 millimeters. So it's a really large breadboard. It contains 8 parts. All of these parts are large parts. So nothing about this is a small fixture, but because of that, they had to break this large complex fixture up into a bunch of pieces. And that means 1, their assembly now has 8 parts instead of 1. And 2, and maybe in a more problematic way, it introduces tolerance stacking. So if each part is off by a little bit and they're all different and you're bolting them on in different places, it basically creates an opportunity for the fixture to end up not being accurate enough to be a successful fixture. So all those things mean that it's an effective fixture, but one that still requires work. So this is where 3D printing comes in. So the solution is that you can consolidate the parts on a larger machine and create a fixture that has a similar function, but has a far superior ease of use and also save some money. So basically, consolidating geometries leads to a few key advantages here. The first is you have one part, and essentially that means it's much easier to keep track of, and assembling the actual fixture itself is much simpler. So if we go back here, you can see that these parts are bolted on to this breadboard in a very specific arrangement. And so you need someone who's skilled and maybe the designer of the tool to actually assemble it in the correct way, because if one of those is an inch off, all of a sudden this fixture is no good. Whereas the single piece end article, you bolt it on all together, it works, it is simple to implement. Second is that it eliminates tolerance stacking. You printed all the parts on the same machine, the tool is physically held together, so suddenly you no longer have to worry about the issues of whether parts are positioned correctly in a micro scale as well. The third is that they feedback from the engineers at Daco said basically that these parts took hours to assemble correctly and test and calibrate. So when we talk about our costs, the cost of 800 versus 500, the material cost is very similar. You're not really saving too much material cost, so you're saving a little bit. What you're really saving is time to assemble, labor to assemble. And that for them is a big cost driver because they have tons of these tools and they need to assemble them as simply as possible. And then the last and most important one is time. So going back to a tool like this took between kind of creating all the parts, designing them specially, setting them up, printing them, executing them, bolting them all on, all that stuff. Took them about 2 weeks to actually complete. So there was 2 weeks from inception to a successful tool. Now, if you compare that to either of the other options, which were likely in the months range, for that, would that be like machining or using kind of traditional erector set type fixturing? It's a huge advantage, but it's still 2 weeks. This 3D printed part comes off the build plate, and it's 2,000 cubic centimeters of material, and it comes off in 3 days. And the size of this part's really impressive. It's 20 inches by 11 by 14. So it's a really big part. You can see that it takes up most of the build volume. And it comes off, it's high quality, it works, and you bolt it on, it's a functional part. So consolidation, as 3D printing, as folks who typically sell smaller printers, we always preach breaking parts apart. And there's a huge advantage to that generally. But if you are able to consolidate, it does bring significant advantages, especially on large parts like this, like inspection tools. So we see, especially in the conformal space or in the space where you have humans interacting it, so large ergonomic tools, those are areas where being able to print a larger single article is a huge advantage. Doug, do you have anything to add or from this?
No, I think you summed it up really well. And I think from a designing perspective, it is nice not to have to break parts up, just from overall time perspective, and the end result typically is better than trying to bolt a bunch of pieces together.
Yeah. And that's the other side of it, is like whenever you have to assemble something, you have to take into account the skill of the assembler. I've assembled things incorrectly many times in my life, unfortunately. And all of a sudden that just gives you, basically every time you create more work for yourself, it also creates another opportunity for error. And if you can eliminate those opportunities for error, you typically are driving towards success in the long run. So yeah, those are our 3 kind of big application spaces. There's obviously more applications. We want to kind of cover 3 in a bit more detail than you would expect from kind of just a quick run through. Before we kind of go to questions and answers, I like to end with this slide, which we've used before. But what you think about this is like, beyond just printing, what makes a successful manufacturing company? So we like to think about it as it's kind of two things. The first is companies that make products with the best user experience. So that means companies that empower their employees to have creative designs, companies that are enabled to iterate many times, because everyone knows here, engineering is basically just an exercise of finding your failures and eliminating them over iterations. And the last one is ones that are able to de-risk, able to find ways to eliminate the risk in their product introduction processes. And then the other side is, from the experience, is the companies that make products with the highest cost efficiency. So that means things like we just talked about here, custom tooling. It means being able to automate flexibly and quickly so that you can make parts thoughtfully and at lower cost. And it means that you always are continuously improving your manufacturing process. Often people, I think a lot of non-engineers think that the design process ends when you kind of lock CAD. And in reality, the design process never ends, right? You're continuously trying to improve how you make the part and the quality of the part and the reliability of the part and all those type of things. And we see generally is with 3D printing, and the FX20 is a function of that. It enables companies to deliver these great customer experiences that customers are really seeking and want at the lowest and most flexible manufacturing costs. And so when you think about 3D printing and why you want to implement it, this is kind of the thesis statement on that for Markforged. And I guess with that, we will open up for questions. I will do my best to proctor. I see 5 already, so I'll open them up. All right. All right, Doug, this might fit for you. So, and it said any switchgear enclosures developed using 3D metal casting. I'm not sure if I know the answer to that.
I don't have any off the top of my head that I can think of. There's obviously a lot of requirements for an application like that. So I would say case by case basis, probably have to know more there to answer it correctly.
Yeah. And then someone else asked, Apart from copper and steel, any other metals have been tried for 3D printing. Yeah, we actually have a metal printer. It's called the Metal X. It's a really cool machine. It's typically best fit for smaller parts. So like kind of thumb to 2 fist size is kind of what we like to think about. We have 6 materials for that. So we have steels, a few different types of steels. We have copper, we have Inconel. Apart from that, we also like have a production solution that's more powder binder jetting. That material, that one has titanium and like a couple different types of Inconel and different mild steels and that kind of stuff. But in general, metal printing, there are like many different materials. Metal printing is almost more constrained by the types of metal powders that are available than the process itself. There are a couple of exceptions, like most people don't print aluminum, although some do because of the challenges it takes printing it. But generally, there is a wide variety of metal printing out there if you're willing to pay for it. Someone said, I don't see supports in the square openings on that last vacuum print. Good eye. So actually, we took photos of this one right off the print bed. So you can actually, if you look carefully, there's supports here and there's supports here. These square openings don't have supports. And the reason that they don't have supports is that if you have inclines of officially 45 degrees, you don't need supports. It basically will just bridge by itself. I say officially 45 degrees because depending on the print setting and the material, you can actually go further than that. So we've actually been experimenting with this. I've been experimenting with this recently. So with Onyx, which is kind of our default black plastic material, it's nylon with chopped carbon fiber in it. It's what all these parts are printed in. In a lower layer height, you can kind of go as far as 65 degrees from vertical without printing and have it bridge. I've been experimenting with what we call turbo mode, but which is really this 250 micron fast printing. You admittedly cannot go as far from vertical. In my experiments, it's been like 52 is where it starts to break down. I'm trying to find the exact number, but yeah. So generally, the material actually can bridge pretty well. Onyx in particular is really good about this because it has a really low coefficient of thermal expansion, so it doesn't warp or curl nearly as much as a typical 3D printing material might. But yeah, so I hope that answers your question. Someone asked, what's the dimensional precision or layer thickness considered in the consolidated and large parts presenting? Doug, do you want to take that one?
Yeah, so the large part.
I think any of the, he specifically asked for the inspection tool, but I think any of the large parts, like generally precision.
Yeah, I mean, precision wise for FX20, we're generally looking at, what would you say, Daniel? Plus or minus 5/1000 of an inch. Somewhere.
Yeah, 5 to 10, depending on the complexity of the geometry, is what I would expect.
And then for layer thickness, some of these parts were printed at the 250 micron layer height and still have exceptional surface quality, but we can go as low as 100 with FX20.
Yeah. So our typical default in a non-FX20 machine is 100, which I believe is about 4,000 for the standard folks out there. And then 250 is about 8,000 by proxy. And yeah, so essentially, we typically go lower layer height on the smaller machines. This one can go larger and faster. I mentioned that this actually prints this material in a slightly elevated chamber temperature. That's just enabling it to print faster at high quality. Someone asked, what are the most economic materials and process what are the most economic materials and processes a waterproof and electrically conductive material that can be used? In terms of waterproofing, you can this material does play all right in water. It's hygroscopic, so it absorbs it. But it can be used in water. You can use any type of coating with this type of material, and that will help seal it. Generally, with FDM printing, especially, being fully leak tight and waterproof can be a bit of a challenge because you're laying down parts within discrete filament pathways. So just by the nature of the process, there's voids they're micro voids that are going to be introduced. So you can do a bunch of things to alleviate that. In terms of electroconductivity, well, these materials are not electroconductive. Typically, they're in metal printing, you can print electrically conductive materials. We don't have any capabilities really in the composite space. A couple of metal questions. Are there any compositions of metals consisting of copper and carbon nanotube materials tried for printing? Not that I know of. There might be. We certainly don't. We typically keep our composites and plastics in one space and our metals in the other. They don't really play well together in terms of printing. Have you developed any platform to print medical titanium alloy? I don't believe that Markforged does. So we acquired a company a few months ago called Digital Metal out of Sweden that does binder jetting, and they can print titanium. I don't believe that it's medically certified, but I'm not 100% sure. Someone asked, this is a good one. Doug, I'll take this to you. For making stamping tooling for prototyping, what materials are needed? Continuous fiber or metal?
Yeah, so in a lot of cases, people are replacing metal dies with continuous fiber reinforced composites. It's going to depend on what material you're trying to bend, if it's aluminum, steel, and then obviously thickness of the material. So depending on what those parameters are is going to dictate whether you need continuous fiber or metal. But in general, composites are a great way to go for bending tools.
Yeah, you clarified aluminum sheets up to 1/8 inch. So if it's aluminum, that makes it a lot easier to bend. I'll say that. One other thing you mentioned that really helps is the idea of a prototype. I think you're hitting the nail on the head there with like production bending tools. It definitely decreases the potential scope of composite printed tools. You probably want to go more towards metal for a high volume production, especially if you're looking for prototype. Like composites can work really well. It could be a really fast solution. Yeah, and I think it's typically a good one.
Yep.
All right. And then do we reverse engineer parts to print? We don't offer it as a service, but we can help with it. And there are a lot of folks out there who do it really well. So there's a combination of scanning technologies. I think we've done a webinar with Kientz in the past could do this. There's also people who just CAD things from being able to from designs or from drawings. So those are both ways you can go. We certainly can print parts, and that's a big advantage of additive is that you can print parts with complex geometries, especially like a good example is like parts that were previously cast that you might need to print or cast or molded. 3D printing can be a better fit for reproducing that type of technology than a mill. Okay, we got a question for. In terms of strength, what standard material, what is the standard material that printed materials with FX20 can be compared with? Doug, do you want to answer that?
Yeah, so our onyx material is going to be somewhere in the neighborhood of 1.5 times the strength of an ABS, something like that. Whereas if you add continuous fibers, you're going to be looking at tensile strengths exceeding aluminum. So it really, I'd say, should cover a broad spectrum. But just to go a little bit further, that's a question we've gotten a lot. And it's one that we've invested in trying to answer. That's why we added simulation to our slicing software, where you can digitally test parts to understand what their strength capabilities are.
Yeah, I'd add an extra shout out for simulation. Essentially, think of it as a very simple but effective FEA engine. But instead of optimizing for the actual geometric design of your part, it's optimizing around the type of way you slice a part. So slicing is in going from your end design to printing. You can basically create different machine instructions for the machine, especially with our technology where you can reinforce parts with fiber in different and creative ways. That basically enables you to customize the strength of your parts, whatever you need. The way I think about it is generally you typically can, like most parts you're printing are not going to be as strong as aluminum, because in order to get as strong as aluminum, you have to add a ton of fiber to parts. But most parts we end up using, or our customers end up printing, are replacing aluminum application. Because there's a huge gulf in strength between like your typical plastic part and an aluminum part. And so where these parts tend to fit really well is that big gap in between. It can replace those parts that maybe you make an aluminum, but only need to be slightly stronger than plastic, or you make an aluminum and they need to be quite a bit stronger than plastic, but you can still reinforce them. So that's kind of the space. Someone asked, what is the fiber volume for the composites? I don't think we share that precisely, but I will take this as an opportunity to explain a little bit more about our carbon fiber strategy. So we use carbon fiber in 2 ways. There's what we use in one way that most people, like most kind of contemporaries in the FFF space or FDM space, use it, and then one way that's pretty special. So the way that we use it, it's typical, is in onyx and in a bunch of other filaments. We essentially add, we call chopped carbon fiber, but what you can think of as carbon fiber powder to the filament as we make the filament. So the filament has basically some percentage of chopped carbon fibers in it, in addition to nylon 6, which is the base material. So the filament itself is actually a composite. And so that is actually something that most people in the industry use now. Most people have a chopped fiber nylon or chopped fiber ABS or polycarb or something like that. So we do that, and that is something we do, and we believe we do it the best. But like the industry can bear that out. And then the other thing that we do that really no one else does is this thing we're mentioning with continuous fibers. So we have that second nozzle, that one in the middle that we mentioned, enables you to lay long strands of fiber inside of layers, replacing parts of infill. So that basically means that you're creating like an internal skeleton for the part that's super strong, that the plastic essentially becomes just a matrix material for that fiber. And you can add however much fiber you want. So that's where we just mentioned simulation and that type of tool. So that's kind of the unique power of Markforged machines. If you're interested, get in touch and we can show you how it works a bit more. I have a program for a part. Will you guys print it? We have a bunch of resellers, so depending on how we can get in touch and maybe direct you to one of our resellers who will often print parts for us. Can the continuous fiber be post machined to be more precise? Yeah, it can be. Doug, do you want to talk about this a little bit? Post processing.
Yeah, I mean, can the continuous fiber be post processed?
I think just generally, can parts be post processed?
Okay. Yeah, they absolutely can. I mean, there's a variety of methods. So just like any normal plastic material, you can machine it, you can paint it, vapor smoothing is another thing that we do, which I'm not going to explain right now, but it's a great post-processing method for improving surface finish of parts.
Yeah, so there's a bunch of ways to do it. You can like sand or machine it. It gets a little bit trickier with composites because they, it's not that easy to machine plastic, but you can. Okay, someone asked, when using fiber, do I need to make it solid fill to be stronger? Yes and no. You can essentially you can add as much fiber as you want within the infill, and that will make the part as strong as possible. Most people who are using fiber don't do that because like the fiber by unit volume is a lot more expensive than the plastic. So we generally think that you add a relatively small portion by volume of fiber, and that gets you pretty far in terms of part strength. And the exact numbers depends on the part and the geometry of the part, so it's hard to give you an exact number. But in general, yes, you can add more to make it stronger, but you don't need to. All right. Someone asked about what is the heat deflection temperature for? Why is the heat deflection temperature for a print drop when adding carbon fiber reinforcement? For example, when using Onyx and Onyx FR, the datasheet show a HDT of 135 for the unreinforced and 105 for reinforced. I think I know the answer for this. I will answer it the best I can, but I'm not 100% sure. So there are two different tests for HDT. I believe there's one that it's like 64 psi, and there's one that's like 264 psi, which is a standard measurement for metric folks out there. But basically, the test is essentially like you exert that amount of force on a part and you heat it, and once it exceeds a deflection threshold, that is considered the heat deflection temperature. So I'm not 100% sure on this, but I believe the reason that it is like this is because the carbon fiber FR was maybe tested at the higher load threshold than the Onyx FR. I'm not 100% sure on that, so don't quote me on it, but I believe that's what it is. But then just zooming out a bit in terms of general HDT and carbon fibers and all this stuff, the reason that the heat deflection temperature does not improve materially with a with this type of when you add fiber actually has much more to do with the way that we print and the plastics than the fibers. So when we're printing, what we're doing is we have basically a toe of fiber that is impregnated with plastic, and that fiber is basically ironed down into the part. But you can imagine if you feel the fiber before you print it, you can actually feel it feels like plastic. And when you heat it up, that plastic becomes more ductile, and the fibers are just kind of along for the ride. So when you look at the fiber inside of our parts, you'll actually see that in some places they'll do basically like a really tight zigzag. And the way you're doing that is you're heating the fiber up to near that plastic's melting temperature and laying it in. And this is just to say basically that when you heat a part up, what's causing it to deflect is not so much the fiber deflecting by itself. It's more that the plastic around the fiber is actually not denaturing, but becoming more ductile, generally enabling the part to deflect. And And the last note on that is, yeah, so that's why you might see something that's a bit different. And that's why it's a bit more complex to talk about HTT in terms of that. Someone asked if we have training once we buy the equipment. Yes, we do have training with partners. Someone asked, do you have applications for oil and gas? Yeah, there are actually a ton of oil and gas applications. We don't have any on here, and I don't know any off the top of my head, but we can follow up with you about that. Someone else asked about the recording. I think Doug maybe took that. We'll email it to you, and it will eventually be posted on YouTube. But I think the faster way is that we email that. All right, I don't see any more questions, so I think we'll cut it off now. I really appreciate everyone coming and listening, and also appreciate y'all staying on for questions and asking great questions. So always great to hear that and get to connect with y'all. So if you have any other questions, feel free to reach out. We'll send the email with the recording pretty soon. You can just reply to that email with more questions, or you can find me. My email is daniel@markforged.com. It's pretty easy. Or you can reach out to Doug. His email's not as easy, but yeah, really appreciate everyone all coming on today. Doug, anything else to part with?
No, I don't think so. I think you did a great job. Thanks everyone. Really appreciate you joining. And if you do want to email me, it's Doug, DOUG.Piazza, PIAZZA at markforged.com. Sorry.
All right. Sounds good. Well, thanks everyone, and have a great rest of your day.